Good morning, everybody. Gonna give people 1 minute to join us for our last live Zoom lecture for Physics 4A. Whoop, whoop. Good morning, good morning, good morning. Wait, this is the last one. This is the last live Zoom lecture. Yes. I will probably, before the final, do a little video lecture that I'll just tape myself and upload, but just doing a little review for the final. But yeah, this will be our last Zoom lecture. And just as people are joining, quick little thing, the quiz, I sent out an email. The quiz that's due on Friday is just going to be on chapter 15. I decided not to cover chapter 16. So the last thing I'm covering is just one little section of chapter 17. Not going to be on the quiz, but will be on the final celebration. And a couple people let me know, Mastering Physics was down yesterday, but it is back up. All right, let's start with, oh, I have so many things open. What is this? OneNote. Okay. So I want to talk just a little bit about waves. And wave is a sort of very interesting concept. If you had to describe a wave, what is the best definition? And I kind of love this definition. It is just a traveling disturbance. It's a disturbance which travels through some medium. And one of the interesting things about a wave is in a wave, the disturbance travels from one point to another, but the material through which the wave travels does not. And just real quick, the material through which the wave travels, we call that the medium. So for example, do a little share here. In a second, we're going to look at the different types of waves. But a transverse traveling wave is the wave that you see up the top here. That's one in which the disturbance, which in this case would be up and down, is perpendicular to the direction of travel of the wave. So like in this case, if I look at this wave, it's traveling to the right. But if I were to look at any part of this, so let's say this is a wave on a string. The string is not traveling with the wave. The wave is the disturbance that's traveling through space. But if I looked at any one particular part of the string, all it's doing is oscillating up and down. This is called a transverse traveling wave, where the direction of oscillation is perpendicular to the direction of travel of the wave. A longitudinal wave is one in which the disturbance is parallel to the direction of travel of the wave. So this, we'll see, could be a sound wave, or it could be a slinky that I'm oscillating back and forth. If I look at this line, it is being disturbed horizontally left and right. That's the direction that the, let's say a slinky is oscillating. The wave is this disturbance which is traveling horizontally, and it is along the same direction of the direction that this thing is oscillating back and forth. So that's what it means to say that in a wave, the disturbance travels, but the medium doesn't travel along with the wave. And this is just sort of a quick little overview. There's three kinds of waves that you're going to study in your physics career. The one that most of us are used to sort of thinking about are mechanical waves. And these are waves that most of you are probably used to thinking about in terms of a wave. You got things like water waves, sound waves, waves on a string. And these kinds of waves can only exist within a material medium. Meaning I can only have sound if there is a medium through which sound can travel. It doesn't have to be air, but that's how we're usually thinking about sound traveling. But sound actually travels faster in a solid, slowest in a gas. So sound will actually travel faster through steel than it does through air. So any mechanical wave, you have to have a medium for that wave to travel through. For sound, it's air or water or steel or something like that. Water waves, it's actually water. Waves on a string would be the wave traveling through the string. In physics 4B, and we'll touch on this a little today, you'll look at electromagnetic waves. And these are oscillations of the electric and magnetic field produced by some oscillating electric charge. All forms of light are electromagnetic waves. And I'll touch on this a little bit, but the only difference between visible light, microwaves, X-rays, ultraviolet is just different frequencies and different wavelengths. Just as a little preview, the one big equation that applies for all waves that we'll talk about is the wavelength of the wave times the frequency equals the wave speed. And one of the interesting things about light waves, in a vacuum, every single light wave travels at exactly the same speed, 299,792,458 meters per second. We usually write this as 3 times 10 to the 8 meters per second. So let me just stop this for 1 second because this is an interesting point. In a vacuum, all electromagnetic waves, all light travels at the same speed. 3 times 10 to the 8 meters per second, which is about 186,000 miles per second. And when you get to physics 4C and 4D, one of the things you'll learn is that the speed of light is the ultimate speed limit in the universe. As far as we know, nothing can travel faster than the speed of light. And in fact, once things start to travel near the speed of light, then you have to start looking at relativity. All sorts of interesting things happen. Time slows down, lengths contract, and things like that. But one interesting thing about the speed of light is it's not infinite, meaning light takes time to travel anywhere. From our sun, light takes about 8 minutes to travel from the sun to the earth. And in astronomy, we measure distances using what's called the light year, which is how far light travels in a year. It's about 6 trillion miles. One of the cool things about this is that when you look up at the sun, you are seeing the sun as it was 8 minutes ago, because that's how long it took light from the sun to travel the however many million miles from the sun to the earth. Well, the nearest star other than our sun is about 4.3 light years away, which means it took light 4.3 years to travel from that star, Alpha Centauri, to the earth. That's the closest star. Many of the stars that you see overhead are tens of thousands to millions of light years away, which means it took light tens of thousands or millions of years to travel through space to reach the earth. Which means if you go camping somewhere out in the mountains where you can see billions, well, you can see many, 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 many stars, there's a good chance that some of those stars don't even exist anymore. They went supernova, they exploded, but since those stars are so far away, the light we see is light that had left maybe 10,000 years ago and is just now arriving. Pretty cool concept. Other interesting thing is, even if I'm only looking at the back of my hand, let's say my hand is 1 meter away, it takes light about a nanosecond to travel from the back of my hand to my eye, which means even if I'm just looking at the back of my hand, I'm seeing it as it was a billionth of a second ago, which means you can never see anything in the present tense. Everything that you see has already happened. If I'm just looking at the back of my hand, it happened a billionth of a second ago. If I'm looking at the sun, I'm seeing light that left 8 minutes ago, so I'm seeing the sun as it was 8 minutes ago. Last concept of this. Hubble Space Telescope has seen a quasar that is about 13 billion light years away, which means the light from that quasar has been traveling through space for 13 billion years and is just now reaching the Earth, or just now reaching Hubble Space Telescope, which means we are literally looking back in time, seeing time 13 billion years ago when the light first left and is now reaching us. Badass concept. Okay. Was that a question real quick?
What's a quasar?
Oh, a quasar is in essence a massive star that has collapsed upon itself, turned into a neutron star, which is spinning incredibly rapidly. And, well, let me just put it like that. It's a star much, much bigger than our sun, which has run out of nuclear fuel. Gravity's taken over. The star has collapsed. and it's not massive enough to collapse into a black hole. It's collapsed into a neutron star. Quick question, if you were on another planet and had a telescope powerful enough, would you be able to see past events like dinosaurs? Ooh, well, here's an interesting point is no, let me think about that. Well, if there was light from the dinosaurs traveling through space, which it has been, yes, there would, let me focus and maybe I'll come back to that. Okay, let's go back to this screen share. What are we doing? PowerPoint. Okay, and the very last one, let me just touch on. If you study 4C and 4D, you'll go into this. It's all about quantum mechanics. But when we're looking at things that are microscopic, like protons, electrons, fundamental particles, and atoms, Newton's laws don't apply. Can't use sum of the forces equals ma. You have to use quantum mechanics. And quantum mechanically, you can never, ever know where an object is. All you can know is the probability that it's a certain spot with a certain probability. So in quantum mechanics, you treat particles like waves. You probably heard of light being treated both as a wave and a particle. Well, electrons can also be treated like a wave. And quantum mechanics is all about how you analyze things like electrons and protons and so on. Okay. Continuing forth with this, why won't this go? Come on, I'm stuck. All right, let's do this again. Okay, so I was kind of mentioning that, let me just do this PowerPoint, Shift F5, screen share. Okay, so again, talking about waves, we generally classify waves into either being transverse, and that's one in which the disturbance is perpendicular to the direction of travel. So like in this case, the string is being disturbed up and down, where the direction of travel of the wave is horizontal. That's called a transverse wave. A longitudinal wave is one in which the disturbance is along the same direction as the direction of travel. So this is pretty much how all sound is produced, is you have an object which is oscillating back and forth. It compresses the air and creates a region of high pressure, and then when it expands, I have a region of low pressure. And it's that pressure wave which is actually moving through the air. And this animation I love, because if you look, it looks like you have a bunch of particles which are actually moving from one side to the other. But if you focus on any one particle, like put your eye just on this little particle here, and you'll see each particle is actually just oscillating back and forth. And in fact, for a sound wave, each air molecule is oscillating back and forth in simple harmonic motion. So every one of these particles, if you just look at one, it just oscillates back and forth. It is not traveling along with the wave. So when I'm talking, my vocal cords oscillate back and forth. That sends this pressure wave through the air, then reaches my eardrum, causes my eardrum to move back and forth. But I do not have air from my mouth then going into your ears. It just causes the air around me to start to oscillate back and forth, and that oscillating sound wave is what's actually traveling. Okay, discard that. Let's go back to OneNote. Oh, stop this for a second. Sorry about that. Technical difficulties, going back to OneNote. Okay, so just a few things about waves. So one, in terms of just things to know about waves. So the big things that we're dealing with for this chapter is just wavelength, frequency, and wave speed. So this might be what's called a snapshot graph, where this would be me taking a picture of a wave at a given time. T equals 0, T equals 2 seconds, something like that. And what I'm plotting is the Y value, the displacement, versus X. And one of the things to know about a wave is what is the wavelength of a wave. So here's a transverse wave. Ooh, look how beautiful that wave is. Woo! The wavelength is really how long a wave is, you can measure a wavelength 3 different ways. So one, the highest point of a wave, depending upon the book, we either call this a crest. Either call this a crest or a peak. Crest or peak. The lowest point, depending upon the book, you either call this a valley or a trough. Wavelength, which we write as lambda, for a regular wave is the distance from peak to peak, which should be the same as the distance from trough to trough, or it's the distance for one complete wave. These should all be the same. So a wavelength is really, in a sense, just how long the wave is. Other thing we often want to know is how big the wave is. The amplitude is sort of considered the height of the wave, and it's the distance from the midpoint of the wave to the highest point, or the midpoint to the lowest point. Frequency of a wave is just how many waves pass a given point in a given amount of time. So let me do a different share. Screen share, let's do, okay. So let me stop this. If I wanted to know the wavelength of this wave, it would be the distance from this peak to the next peak, the distance from one trough to the second trough, or it's the distance of one complete wave. If I wanted to know the frequency, and if I was standing right here, and I count how many waves per second pass a given point, that's the frequency of a wave. Okay, going back to OneNote. I'm not going to derive this for you, but I just want to mention this equation I wrote before is the one big equation that holds true for every possible kind of wave. And it says the wavelength of the wave, which is just measured in meters, times the frequency of the wave, which is measured in hertz, equals the wave speed, which is in meters per second. So if I were to go back to this thing here, my wavelength would be the distance from peak to peak in meters. Frequency would be how many waves are passing a given point in a given amount of time. And wave speed is how fast the wave is moving, in this case horizontally, in meters per second. So if I could track how fast this particular peak is moving in meters per second, that would be my wave speed. So like I was saying, for light, the speed of light, so for light, what we would have is the wavelength of light times the frequency of light equals the speed of light, which in a vacuum is 3 times 10 to the 8 meters per second. So from this equation, I have an important clicker question for you. I kind of want to do this as a poll. So this is clicker question 16.3. So again, our big equation is wavelength times frequency equals wave speed. So the question is this: a source of frequency f sends waves of wavelength lambda traveling with speed v in some medium. Could be water waves, could be waves in a string. So the question is, if you double the frequency of the wave, so it's changed from f to 2f, what's going to happen to the wavelength? What's going to happen to the wave speed? So when I double my frequency, how does that affect the wavelength? How does that affect the wave speed? And let's try this as a poll. All right, so I've launched a poll. You've got 5 different choices, A, B, C, D, E, for what happens to the wavelength and what happens to the wave speed. What do you think? Double the frequency of a wave, what happens to the wavelength of the wave? What happens to the wave speed? What do you think? I'm going to give people 30 seconds to think about it. Right now, we've got the majority say E. Wavelength is cut in half, wave speed doubles. followed by C. And a little hint so far, the majority does not have the correct answer. Ooh, does anybody want to change your mind? I'm not even sure. Can you change your mind on these polls?
Nope.
Nope. Okay. All right, well, let's just stop this and end the suspense. Let's first share the results. About 43% say E. The wavelength would be cut in half. The wave speed would double. Here's something to think about. If the speed of sound depended upon the frequency, then concerts, music would never, ever, ever sound the same because different frequencies would travel at different speeds. So say you went to a concert and you got, a 10-piece band. The guitar is going to have a different frequency than the drums, which is going to have a different frequency than the singer, which is going to have a different frequency than another instrument. If all those different frequencies traveled at different speeds, then all of those sounds would arrive to you at different times. You would never have all of the sound frequencies arriving at the same time to produce music. Or even thinking about light. We're not going to really cover this, but you guys probably know the spectrum of visible light is Roy G. Biv. The only difference between red light, green light, and blue light is different frequencies, different wavelengths. So red, orange, yellow, these are sort of considered low frequency visible light. Blue, indigo, and violet is higher frequency visible light. But if different frequencies of light traveled at different speeds, and let's say you walked into a room, then you might see your hair at a different time than you see your eyes, at a different time than you see your shirt, if they all traveled at different speeds. So here's the cut to the chase. The correct answer is, if I double the frequency, the wavelength will cut in half, but the wave speed doesn't change. For a particular wave speed only depends upon the properties of the medium. So for example, the speed of sound in air depends upon the temperature. Sound travels faster in higher temperatures than low temperatures. But at a given temperature, every sound wave will travel at the exact same speed. A higher frequency sound wave will have a smaller wavelength. A smaller wavelength will have a higher frequency. So I have this in the notes, but I'll write this real quick. V is only determined by properties of the medium. For sound, it depends upon the humidity, it depends upon the temperature, things like that. But at a given temperature, all sound waves will travel at the same speed. What determines the frequency of a wave? All waves are created by something which is oscillating up and down. The frequency of the oscillating object will be the same as the frequency of the wave that it produces. So whatever produces the wave determines two things. One, the amplitude of the wave. Two, the wave speed. So frequency is determined by the wave source. And that also determines the amplitude. And so in a sense, the wavelength is the dependent quantity. So the wavelength will be given by the wave speed divided by the frequency. Wave speed only depends upon properties of the medium. The frequency is determined by whatever is creating the wave. So you don't need to know these exact things, just as a preview. Speed of light in a material depends on something called the index of refraction. And what it really is the index of refraction is just given by the speed of light in a vacuum divided by the speed of light in the material. So like water has an index of refraction of 1.33, which means the speed of light in water would be equal to the speed of light in a vacuum divided by 1.33. All forms of light in water would travel at the same speed. It's just that higher frequencies mean smaller wavelengths, smaller frequencies mean bigger wavelengths. This is something that I would have covered had we had more time. For a wave on a string, how fast a wave travels on a string just depends upon two things: the tension in the string and what's called the linear mass density. We're not covering this, but the speed of sound in a material depends upon something called the bulk modulus divided by the density. Again, you don't need to know that, but every sound wave in a given medium travels at the same speed. Bigger frequencies means smaller wavelengths. So let me see if I can just show you a cool little demonstration of this. I have too many things open. Let's try interferent waves on a string. Okay, so here's a wave on a string. I play this. I have this thing oscillating up and down. If it oscillates up and down at a low amplitude, that's going to create a low amplitude wave. If it oscillates up and down at a big amplitude, that's going to create a big amplitude wave. The frequency that it oscillates up and down at will determine the frequency of the wave. So here is a higher frequency wave. Here is a lower frequency wave. You can see that higher frequency waves end up giving me a smaller wavelength. So if I were to measure the distance from here to here, that would be the wavelength of this wave. If I then increase the frequency, what I should find is that I get a smaller wavelength. So the distance from peak to peak is going to be smaller. The wave speed would be how fast this wave is traveling. So if I timed how long it took one of these pulses to travel a certain distance, that would be my wave speed. But it only depends upon the properties of the material. So like in this case, if I could vary the tension, lower tensions in a string means less speed. So if I change the tension, this should have a smaller wave speed. All right, that's getting a little bit funky. While I'm here, let me just show you how all radios work. Let's share this. So this is a cool little thing from FET. So all radio stations work the same way. They have a transmitting antenna. The antenna has a bunch of free electrons in it. What happens is, let's oscillate this. Oscillate. You have in the antenna a bunch of electrons that start to oscillate up and down. That oscillating electron will create oscillating electric and magnetic fields. That radio wave will then travel out through space, and then when it hits your antenna, and this could be the antenna of your car, the antenna of a radio, it's going to cause electrons in the antenna to start to oscillate up and down. A higher frequency wave just means that these electrons are oscillating up and down more rapidly. And one really interesting thing, you may know this, but FM stations, what's a good FM station? 95 points, what's KPIG? 104.3? Anyway, 104.3 FM. FM is really 1,000,000 hertz. So if you had a radio station of 104 FM, that's really 104.3 million hertz, which means the antenna that's producing that frequency radio station has electrons in it that are oscillating up and down 104.3 million times a second. Pretty interesting. Okay, so going back, the big point to this is that wavelength times frequency equals wave speed. Frequency is only determined by frequency is determined by whatever's creating the waves. The wave speed is determined only by the properties of the medium through which the wave is traveling. And then the wavelength is sort of given by the wave speed divided by the frequency. Okay, I want to stop this for 1 second. Kind of want to see someone try and model a world where the speed of light isn't constant. You could scroll up a little bit more. Okay, let me just open it up real quick to any questions that I've covered so far. So, different kinds of waves. A wave is just a disturbance which is traveling through a material that we call the medium. In a wave, the disturbance travels, but the medium doesn't travel with the wave. So if you were to look like an ocean wave, the water is not moving along with the wave. The water is just moving up and down. The wave is the disturbance that's traveling through space. All waves are created by something which oscillates up and down. The frequency of a wave is determined by whatever's creating the wave, the frequency it's oscillating at. The wave speed is only determined by the properties of the medium through which the wave is traveling. And then the wavelength depends upon the wave speed and the frequency. So we just pause for 30 seconds, see if there's any questions. If not, then the one thing I'm going to cover from chapter 17 that you would need to know is really just interference. And I'll touch on that in a second. Wind speed also be relative to the observer where it is measured, like if you have two cars colliding relative to each other. So how fast the wave travels through the medium doesn't depend upon who's observing it, but because of relativistic effects, they could measure a different speed than the speed that the car is traveling at. Meaning, if you got a car traveling at 50 miles an hour, that's 50 miles an hour relative to somebody who's stationary relative to the car. But if I'm measuring the speed in another car going the opposite direction, I'm going to measure a different speed than the car is traveling, but that doesn't affect the, well, let me just stick with that. Okay, very last thing. Before I go through interference, I have a question for you. It's going to be a challenging question, so pay attention. Are you ready? Question is this: can these two pens exist at the same place at different times? The answer is sure. It's here. Same place, different times. Can these two pens exist at different places at the same time? Sure. Different places at the same time. Now here's the fun part. Can these two pens exist at the same place at the same time? And the answer is no. Physical objects that have a mass, that have a volume, cannot occupy the same space at the same time. However, waves can. And when two waves exist at the same place at the same time, they interfere. Can you show the speed of light and material is given by the equation again? I'll get to that real quick. I just lost my train of thought. Oh, two waves can exist at the same place at the same time. And when they do, they interfere with each other. Just as a quick little example, in your car radio, you can probably pick up, what, 50, 60, 100 different radio stations? That means at the location of your antenna, there are 50, 60, 100 different radio waves all existing at the same place at the same time. And what your car radio is doing is just preferentially picking out one of those frequencies over all the others. So two waves can exist at the same place at the same time. And when they do this phenomenon called interference. And let me just quickly show you what that looks like. Waves, which one? Too many things open. Let's go with this one. No. Sorry, stop that share. Do a new share. Is it this? Okay, so here are two waves traveling in opposite directions. So you got the red wave traveling to the right, the blue wave traveling to the left, and below is the sum of those two waves. So I'm just adding those two waves together. Well, this is showing you what would happen if these two waves, whoops, let's redo this, reset. If these two waves were at the same place at the same time. So imagine these two waves, I mean, the image is showing them on top of each other, but imagine they're at the physical same location at the same time. A wave is just a disturbance. And so if I want to know what is the result of two waves being at the same place at the same time, I just add those two disturbances together. So in this case, the first wave has an amplitude of 20 centimeters. The second wave has an amplitude of 20 centimeters. If they're at the same place at the same time, I simply add the two disturbances together. So the end result is I get a wave here which has twice the amplitude. We call that constructive interference. The end result is a wave with a higher amplitude. Well, I could also have two waves traveling in opposite directions. So again, this wave, the red one is traveling to the right, the blue one is traveling to the left. Down at the bottom shows the sum of these two waves. Well, if they're at the same place at the same time, Let's step through. Mathematically, what you do is you just add the two disturbances together. So if in the top wave, this one is at a disturbance of plus 20, this one is at minus 20, when I add these two together, they cancel each other out. That's called destructive interference. And that's really sort of just how waves work, is waves are just disturbances. And if I have two disturbances at the same place at the same time, I just add them together mathematically. It's called the principle of superposition. Let's just pull that up for a second. Okay, so let me stop that and then just go to the notes. So I was going to mention this. So this is how noise canceling headphones work. Well, I mean, I'll come back to that. So the answer is 100% yes. How much detail? I'll just touch on it now. Well, no, I'll come back to it. But real quick, every noise canceling headphone also has a microphone, because what it's doing, it's recording the external noise. The circuitry in the headphones are in essence taking that sound wave and flipping it upside down and then sending it into the headphones at the same time as you're hearing the external noise. So you have the recorded noise, the circuitry flips that sound upside down in a sense, gives you the mirror image of it, and then sends it into your headphones. And those two sound waves that are exactly opposite will cancel each other out. It's really wild. And if you have a really good set of noise canceling headphones, it's pretty damn cool. Okay, so going back to this, let me just skip ahead. So we call this, well, one, when two waves exist at the same place at the same time, they will interfere with each other. And the end result can either be a bigger wave or a smaller wave. We call it the principle of superposition. And it's just a fancy way of saying you just add the disturbances together. So it says this: when two or more waves exist at the same place at the same time, the resultant disturbance is the sum of the individual disturbances. So I can't easily draw two waves existing at the same place at the same time. But let's say I had these two waves that were both at the same place at the same time, and I want to know what is the end result. What I would do mathematically at every point, I'd add the disturbance at this point to the disturbance at that point, and that tells me what the sum is. I add the disturbance at this point to the disturbance at this point, that tells me what the result of the interference is. The end result is if I have two identical waves at the same place at the same time, I'm going to get what's called fully constructive interference. The end result is going to be a wave that has twice the amplitude of either wave. And if we're talking about sound, the end result would be a louder sound. If we're talking about light, the end result would be a brighter light. Now, we say that they are exactly in phase in terms of the mathematics of waves. It just means that the peaks and the troughs are all exactly lined up with each other. Now, you could also get what's called destructive interference. And that's when the waves are what's called exactly out of phase. In essence, you have the peak of one wave lining up with the trough of another wave. And again, if I add these all mathematically together, so I add this point to this point, the end result would be 0. I add this point to this point, the end result would be 0. I add this point to this point, the end result would be 0. So if these two waves existed at the same place at the same time, the end result is I get fully destructive interference. And in essence, what I'm getting is these two waves exactly canceling each other out. So two waves simultaneously in the same spot at the same time that are identical. So if I could add this wave to this wave, and again, imagining these are at the same place at the same time, I'm going to get a wave, same frequency, same wavelength, but the amplitude would be twice as much. We call that fully constructive interference. On the other hand, if these waves are mirror images of each other, so when one wave is peaking, the other one is at a minimum, and I add these two together, the end result is complete cancellation. If we're talking about sound, you would literally hear no sound at all. And if you're talking about light, you would see nothing, complete black. And just as a little preview for those of you taking Physics 4C soon, there's something called the two-slit experiment where you can actually pass laser light through two slits. And what's going to happen is that laser light is going to create an interference pattern on a screen. And what you're going to see is you'll have region, let me do a different color. You'll have regions of so what's happening is light's coming in, and depending upon how far the light travels, I can get regions where I'm going to get constructive interference, where I get a bright spot, and then there'll be regions of destructive interference, and then constructive, and so on. So you can actually have light canceling out light, which is a really cool concept. So what you're doing is passing laser light through these two really small slits. It forms an interference pattern. Where you have a bright spot is where you have constructive interference happening. Where you have a dark spot is where you have destructive interference. Okay, so let me just stop this for 1 second. There's only really one equation for this chapter besides wavelength times frequency equals wave speed. I'm going to get to that in 1 second. But I just want to open it up to any questions about interference. It happens with any kinds of waves. But they have to be identical. Like you can't have a sound wave interfering with a light wave. But if I have two light waves, two sound waves, two water waves at the same place at the same time, they can either interfere with each other to produce a bigger wave. We call that constructive interference. They can interfere to produce a smaller wave. We call that destructive interference. And they could actually fully destructively interfere where there is no wave at that moment. Questions I can answer on that? Okay, and one other quick thing I want to just mention before we move on. Am I sharing this? Shift F5. Okay, so the waves only affect each other when they're at the same place at the same time. But other than that, they do not alter the travel of the other wave. So this is just an animation showing two waves traveling in different directions. When they're at the same place at the same time, they interfere with each other, and you just add the disturbances together. But that's only when they're at the same place at the same time. Other ways, they are not altering the motion, the direction of travel of the other wave. It's so they're moving in opposite directions. When they're the same place at the same time, they interfere, but then they keep on traveling as if they had never interfered to begin with. So mathematically, if we were doing this live, there's equations that you can do for waves with sines and cosines and adding them up. But again, the end result is if these two waves were at the same place at the same time, and I want to know what is the result, I would take, all right, add this together, and that gives me the result of these two waves at the same time. I add this together and add this, and that gives me the result, and so on. So you're just mathematically adding the two waves together. And then again, oh, I don't have it here. So it can either be constructive interference or destructive. So last thing I want to talk about is just this one equation for it. And let me just do a little drawing here. Let's say that I have two speakers that are emitting identical sound waves. Whoa. Somebody drawing on my screen here? All right, let me stop this for 1 second. Share screen, one participant, advanced sharing options. Who can share? Only host. All right, take that. Okay. 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 All right, now somebody's messing with me. Why? Oh, is that you, Mary? Okay, going back to this share screen. If I have two, let's say, speakers that are emitting identical sound waves. So these are emitting sound waves that have the exact same frequency, same wavelength for both. depending upon where I am, I could hear interference, because even though these waves start off in phase, if they travel different distances, they can arrive out of phase. And let me just show you a couple really great animations for this. Let me just tell you let me show you. Stop this share. Share this screen with, okay. You can see this sort of so here are just two sources of waves. These could be water waves, they could be sound waves. They're emitting identical waves. If I am right in between them, so they travel the same distance to reach me, I'm trying to get it, then those two waves are always going to be in phase if they start in phase. So I've got two speakers maybe emitting sound waves. If I'm the same distance from each speaker, they are always going to arrive to me in phase, and they're going to produce constructive interference. If, on the other hand, I am one wavelength farther away, so here I'm one wavelength farther away from this source than I am from the other source, they will still arrive to me in phase because that first wave has traveled one wavelength farther. I'm still going to be peaking at the same time as the other wave. If I travel two wavelengths farther from one source than the other, they are still going to arrive to me in phase. So what matters is how much farther one wave travels than the other. If they travel the same distance, they're still going to be in phase. Now, when would they be out of phase? If one wave traveled a half a wavelength farther, then these two waves are going to arrive at this point always out of phase. Meaning when one of the waves is peaking, the other one's going to be at a minimum because it's one half of a wavelength farther. So in this case, I'm half a wavelength farther from this wave source than I am from this one. So at this point right here, they're always going to arrive to me out of phase and produce destructive interference. If I'm right here, I am now 1.5 wavelengths farther from one source than the other. It's still going to arrive to me out of phase. Or if I'm right here, now I'm 2.5 wavelengths farther from one source than the other. They're still going to arrive to me out of phase. Another way of seeing this, let me stop this one. I really like this. Let me share this one, share screen. Here's a different way of seeing it. So again, these are two sources of sound, or light waves or something like that. If I'm right in between them, so they travel the same distance. Let me get it exactly right. So what this is, AB minus BP. So AP is the distance from P to this source. BP is the distance from P to this source. If they travel the exact same distance to reach me, they're going to be in phase. These two waves are going to add together to produce a wave that has twice the amplitude. Or if I'm one wavelength farther from one source than the other, get it just not close enough. Here, I'm about one wavelength farther from one source than the other. They are still arriving to me in phase. Or if I'm 2 wavelengths farther from one source than the other, it's going to arrive to me in phase. But if one of the waves travels a half a wavelength farther, or 1.5 wavelengths farther, or 2.5 wavelengths farther, then they're going to arrive to me out of phase. So if I'm right here, oh, look at that, it's beautiful. I am a half a wavelength farther from source A than I am from source B, which means these two waves are going to arrive to me out of phase. I'm going to get destructive interference. If this was sound, I could walk anywhere along this line and I would hear absolutely nothing. Or if I'm 1.5 wavelengths farther, close enough, from one source than the other, again, fully destructive. Now, it's also possible that it's not fully destructive or fully constructive. So if I'm somewhere here, This is not fully constructive where I have twice the amplitude, but it is more constructive than destructive. Okay, so looking at this mathematically, what matters for interference is how much farther you are from one source than the other. So what we talk about is called the path length difference. And that is the distance you are from one source minus the distance you are from the second source. So here, if these are two speakers and they're emitting identical sound waves, R1 would be my distance from the first speaker, R2 would be my distance from the second speaker. What I was just trying to show you is that if delta R is 0, or 1 wavelength, or 2 wavelengths, or 3 wavelengths, then I'm going to get fully constructive interference. They are going to arrive to me at exactly the same point along their cycle. Either they're going to be peaking at the same time or a minimum at the same time. On the other hand, if the path length difference is a half a wavelength, or 3 halves, or 5 halves, ... we call that fully destructive. One interesting point, I went to the very first concert they ever had at the new Giant Stadium. I think it was the first one. It was Bruce Springsteen. I got free tickets. Not that I don't like him, but I probably wouldn't pay to see him. But anyway, the point is, I went to the concert, and after about 45 minutes, we got up to leave because it was the worst sounding concert I'd ever heard. Just the sound was all garbled. And in the process of trying to leave, we moved about 1,000 feet, and it was like night and day. The sound was crisp and clear and things like that. It ended up that they didn't really look at the speaker positions well enough, and at a certain part of the stadium, you had interference happening from the different speakers in such a way that the sound was completely garbled and it was just not well designed. And in the process of just moving maybe 1,000 feet, it was like night and day. So if we were doing this live in class, what I would do is I would play, let me just do that here. If we were doing this in class, you know, up at the front of the board, we've got the little speakers mounted to the wall. What I would have done is played a pure note out of each speaker and had you walk around the room. And depending upon where you are, you'd find spots in the room where there was constructive interference happening and the sound would be much, much, much louder. And there'd be spots in the room where destructive interference was happening and it'd be much, much, much lower. So what I would care, so if you were right here, what you would care about is, what is your distance from this speaker? Call it R1. What is your distance from this speaker? R2. Your path length difference is just the absolute value of the difference, just so it doesn't matter which one that you do first. Whether or not that produces constructive or destructive interference depends upon the wavelength of the light. If this path, or wavelength of this sound, if this path length difference is 0 or 1 wavelength or 2 wavelengths, then it's fully constructive. And if that difference is a half a wavelength or 3 halves or 5 halves, ... that's fully destructive. I'll get to your question in 1 second. You have probably never noticed this in your room when listening to your music on a stereo or something like that. How come you never really hear this? And what ends up happening is music is a mixture of many, many different wavelengths and frequencies of sound. If you're at a certain location of your room, it's possible that one of those frequencies could undergo interference. But music is a combination of many frequencies being played together, and it'd be hard for us to pick out one frequency which is louder or less loud than it usually is. But if you've got some way of playing a pure note out of your speakers, like from a tuning fork, a pure A note or a pure B note, then you can walk around your room and find certain spots of your room where constructive interference is happening and the sound is much louder, certain spots where destructive interference is happening and it's much lower. Okay, let me just check on the question real quick. So does blending colors of light work by interference, combining the two waves in a way it resembles a specific frequency? No, that works more with how our eyes and rods and cones in our eye react to light. So let me not just sort of go into that. Is that why surround systems were made? Ooh, that's a good question. I don't know if that's the specific reason, but it's just, it's nicer to have sound coming in all directions. Robert, did you have your hand raised? You have a question?
Yeah, I was thinking about that situation in a giant stadium. Is there some way we could troubleshoot that, or like how would you fix that problem?
Well, there's a whole science of physics called acoustics, and really nice concert halls, they will spend thousands of dollars getting acoustic engineers to really look at the placement of the speakers, where people are going to tend to be sitting, so that there are no what's called dead spots in the concert hall. And a dead spot would be, you know, if I've got 5 speakers, there could be a room or a section of the room where 4 of those speakers, just because the distances is just right, is producing destructive interference. So I don't know, I haven't been to another concert there, but my guess is that somebody figured it out and then changed the location of the speakers and distance away and things like that. So yeah, there are ways of doing it. I wouldn't know how to fix it unless I knew the specific frequencies that were being emitted and things like that. Wavelength for sound waves. What's a ballpark wavelength for one other thing I forgot to mention, let me just write down real quick, is some problems you want to know what the speed of sound is. And speed of sound does depend upon temperature, but generally, if you're not told otherwise, the speed of sound is about 343 meters per second, and this is at 20 degrees Celsius. So if you were ever needing a speed of sound in a problem and you're not given it specifically, 343 meters per second is sort of the speed that you use. And I had one other thought about this. What was it? Oh, just real quick, just in terms of just waves traveling. Speed of light is so fast that you can almost consider it infinite for things that are close by. The reason why you always see lightning before you hear thunder is just because the speed of light is about 1,000,000 times faster than the speed of sound. And speed, so one mile, just real quick, is about 1,609 meters, which if you're traveling at 343 meters per second, means it takes sound about 5 seconds to travel 1 mile. So we don't get a whole lot of lightning and thunder out here, but if you ever see lightning and you start counting, if you count 5 seconds between when you see the lightning and you hear the thunder, that means that lightning was a mile away because it took sound about 5 seconds to travel the 1 mile between the lightning and you. And if you've gone to a baseball game and you have nosebleed seats, even just that distance is far enough away that oftentimes you'll see the bat hit the ball, and then a split second later, you'll hear the crack from the bat, just because the speed of sound is so much slower than the speed of light. You know what? I just went over by a bunch. I'm just making an executive decision. Chapter 17, I'm not going to have on the final. The homework is, don't worry about it. I wanted to cover all of this conceptually because in Physics 4C, you're going to be doing interference of light. And in Physics 4B, you're going to be looking at, well, a little bit of electromagnetic waves, but I just wanted to cover it conceptually. So this lecture is just sort of a bonus lecture for getting you ready for some stuff in Physics 4B and 4C. It will not be on the final, and your quiz on Friday is just chapter 15. Does sound travel faster at sea level? So let's think. Speed of sound depends upon, I never actually thought about that. Let's, speed of sound depends upon something called the bulk modulus divided by the density. As you get higher up in the air, air gets less dense, which means the speed of sound would generally be greater. So my first thought is the speed of sound is going to be greater near sea level. And in fact, I know that to be true because if you're trying to break the sound barrier, so one, sound barrier is not like a barrier. It's not like you can't go faster than the speed of sound. But as you start to approach the speed of sound, the sound waves start to pile up on each other. And when you hear about such sonic boom, that's just all of these sound waves piled up on each other. And then once those piled up sound waves hit the ground, there's a tremendous amount of energy associated with it. It can knock down trees, it can blow out windows and things like that. So the point is, if you're trying to break the sound barrier, sometimes they will do that at higher altitudes where the speed of sound is less than at lower altitudes. For chapter 15, will you post Tuesday's lecture? Oh, so the lectures are already posted on the YouTube playlist. I just haven't had time to link them yet on the physics resources page. So they are on there. Check out YouTube. If I can, I'll do that as soon as possible, but I have to get my daughter in like 15 minutes. But yeah, they will be up there tonight. Final celebration will be on mastering physics. I will hopefully make a video on Friday or Monday just as a little review. It will be comprehensive. It'll be like the final, or it'll be like the second celebration where it'll be mostly multiple choice with some short problems where you have to fill in the answers yourself. So I'm going to end lecture, bring in office hours. So again, chapter 17, I just decided I'm not going to have on the final. I wanted to cover it conceptually just so you're ready for that when you see it in Physics 4B and Physics 4C. So the final will only be up to chapter 15. It will be on Wednesday. So what I think I'll probably do is have it available Wednesday morning starting at 8. Has to be done by 11:59 p.m. on Wednesday night. Like before, it'll be open book, open notes, no internet searches. It will be comprehensive, and I'll try and prepare a short little review video just telling you the most important things and things you don't need to study. That was it. That was the last Zoom lecture. Thank you, everybody who's been joining me live for these Zoom lectures. It's not the real thing, but it's definitely nicer talking to people than just sitting here at home recording a video. Thank you, everybody, missing everybody in class. Thank you to everybody that did a live Zoom presentation. I haven't gotten a chance to read the formal reports that were emailed to me or watch the videos, but everyone who presented on Zoom did awesome. It was great. Thank you, everybody. Any questions I can answer on thank you, thank you, thank you. It was fun. It was an interesting semester. Hopefully we'll be live in the fall. Don't know yet. Either way, I'm going to be on sabbatical, so I won't be around in the fall, but I'll be back in the spring. Thank you. I'll stick around for another 12 minutes if anybody has any questions. If not, thank you for joining. Thank you for being a part of Physics 4A. I hope this online transition wasn't too hard, and hopefully we'll be back live as soon as possible. Stay safe and healthy. Thank you. Anybody got any office hour questions I can answer? No questions? Oh, we got somebody coming up. Kenny.
Yeah, I was just going to ask, kind of tangent to what you're talking about. You were saying that the light waves travel at the same speed through a medium, no matter what the color of the light?
I realized as I said that that's not true. If that
Okay.
was true, if that was true, there wouldn't be dispersion.
Right.
So in reality, red light travels at a slightly different speed than blue, at a different speed than violet. How much light bends in going from one transparent material to another depends upon how fast that light is traveling. So yeah, I realized as I said that that's not right. different colors do travel at different speeds and different materials.
Okay. I used to design fiber optic systems, and that was one of the things that a lot of people would get caught up on, is the different frequencies of the lasers would actually arrive at different times at the other end. So they had to do a thing called pre-emphasis or de-emphasis, and I've seen them do that in sound systems too, to kind of emphasize certain sounds so that they travel farther at the same decibel rating, because there's a attenuation happens through a medium that is affected by frequency.
Right, so you would, in essence, slow down the faster traveling light so it arrives at the same time?
Yeah.
Oh. So that's going to depend on how far it travels. So you have to first know exactly how far the light is going to travel so you know how long to slow it down for?
Yeah, and so like when we were designing the fiber optic system around the Bay Area, how long it takes for light to get from Napa to Santa Clara at the different frequencies would make a big difference.
Oh.
And if you think about the way that they send data packets, it's either on or off, and it's like in a little burst. So think of it like a square wave, and the farther you go, the edges of that square wave start becoming rounder and rounder, and then you reach a point where the previous wave is starting to interfere with the existing wave, and you end up with just noise. So yeah, it totally beyond the scope of this class and probably anything that's taught at Cabrillo, but it was just like, I thought you might think of that as interesting. So.
And were you telling me, I think I was saying that a lot of communication now is done with fiber optics, but they're not using fiber optics anymore.
Oh,
is that
no.
a conversation I had with you?
They are using fiber optics. Anything that goes through satellites has to go up to geosynchronous orbit and back. That's why, they're trying to put in these low Earth satellites so that latency is much faster.
Oh, that's what it was. So they're doing less where they're banking something up to the satellite and then back down and doing more stuff using fiber optics.
Yeah.
That's
it's all the speed of light, but I mean, to go from Earth to geosynchronous orbit and back to Earth, which is 23,000 miles up and back, you're looking at almost 50,000 miles round trip at the speed of light, which is quick.
I was going to say, that can't be that. So that timing, that little bit of time difference is enough that we want to use fiber optics rather than all of these satellites that we have?
Oh, yeah, it really is. It's huge. Those nanoseconds are incredibly, well, it's the difference between the dial-up speed on your phone and your high-speed internet. You could go with a dial-up phone and go to space and back, but with a high-speed internet, you're trying to get more data in less time. So each of those little slices are a lot thinner.
Got it. Now your phone uses Morse code, right? Is that what
That's why it takes me so long to text.
Marco, yes, at some point I'd love to talk climbing with you and the physics of climbing. So obviously I'm going to be around all summer. So yeah, we can totally do that at some point. And maybe even if, they open stuff up, they can go climbing together. There's actually quite a few physics students that are climbing. It'd be fun.
That would be awesome.
Yeah, it'd be fun once the gym opens up again. I know they were going kind of regularly, and I have all this trad climbing gear that's just sitting in my garage getting dust, so I'd love to use it.
Okay, sweet. Yeah, well, I'll definitely I have your email, so I'll email you once Castle's open or something.
Super, that'd be awesome.
All right, sweet. Have a great summer. Thank you.
You too, Marco. Take care.
You too.
Bye. Tim or Mary, any questions from either of you?
Yeah, could we briefly look over exercise 2 in the chapter 15 homework? Part B of it, I just had a question with, I guess, figuring out what your initial phase angle.
Let me see, what's the easiest way to look at this? Homework assignments, individual chapters, chapter 15. All right. And I only literally have 2 minutes. All right. Screen share. Okay. Chapter 15, which one?
Number 2 in exercises. And in solutions, it just that phi naught was 0, and I don't know why. I guess is
An air track glider is attached to a spring. The glider is pulled to the right and released from rest at t = 0. It then oscillates with a period of 2 seconds and a maximum speed of 40 centimeters per second. What is the amplitude of oscillation? So here they just specifically said that you're pulling at a certain distance and then you're releasing it from rest, which means your initial velocity is going to be 0. Was that your question?
No, your phi initial was 0. Your like angle, your phase angle.
Oh, it's so you want to know
Why it's 0? Because like when I calculate it, I get something like, I don't know.
Okay.
Whatever.
So let me stop this there. So you're told that basically it's being pulled. So let me just do a quick little share. Screen share. So in essence, you know that you're pulling this some distance and then releasing it from rest. So if you release it from rest, the distance you pull it is going to be the amplitude, right? You can't pull it, release it from rest, and then have it go farther than you pulled it from. So which means that at t = 0, you have x = a and v = 0 because you're releasing it from rest. So you know that
that makes sense.
position as a function of time is a cosine omega t plus the phase angle. And so at t = 0, we have x = a. So if I plug in t = 0, I get a = a cosine of the phase angle, which means that I want the cosine of the phase angle to be 1, which means my phase angle is going to be either 0 or pi. Oh wait, sorry, phase angle is going to be 0.
0 or, yeah.
So yeah, you're really just looking at what is my initial position at t = 0. And then if you need to decide between 2 different angles, then you're looking at the velocity. And is the velocity positive or negative at t = 0?
Okay. All right. Thank you.
Sound good?
Yeah.
All right. Tim, any questions from you, Tim? Thumbs up meaning question or no question?
I think that was our question.
All right. All right, then I am ending office hours. Thank you, everybody. Good luck. All right, I'll talk to you later.